Hi, and welcome to the lecture on scientific method and experimental design. This is meant to introduce you to a way of thinking and to give you insight into how we design different experiments throughout the year. Scientific method, there's many different ways to look at it. I think this is a way that works well for most of the students in high school, and it's called the OTAC for everyday living. That is, you observe, you hypothesize, you test, and then you analyze, and then you finally conclude. So those are the 5 steps in the process, and we're going to take the time to go through each one of them. Observe. That is probably the most important step in the scientific method, because if you don't observe carefully and accurately, the rest of the process is flawed. Albert St. Georgi is a Nobel laureate who has made many interesting discoveries in his career. This particular quote appears on the wall at the Marine Biology Labs in Woods Hole. Discovery consists of seeing what everyone else has seen and thinking what no one else has thought. So if you make careful observations and think about them, you may in fact be someone who makes a huge breakthrough. So observing isn't just writing down numbers in a table. It's about making notes and drawings as you go through the experiment. They're personal records. There's a way to share your ideas and your observations with others. It can be numbers, it can be sketches, as long as what you're writing down is accurate. And so here's some examples of very famous journalists, even though you might not think that's the case. This is watercolor from Albrecht Dürer, who was a famous artist back in the late early 1500s. And he made this rendering of grass and what we would consider weeds. Ecologists today can then look at this and they can tell you what time of year it was, what the kind of soil was, where this grew. So there's a lot of information contained in that, what we would consider simple drawing. And here we have, of course, Michelangelo. This is an anatomical study. Michelangelo was meticulous in his detail. He actually dissected corpses to get a sense of muscles and muscle attachments so that he could render fairly accurate anatomical drawings. In fact, he was so meticulous that he drew heart valves in such a way that he was able to explain how blood moved through the heart. And it wasn't until the 1950s that a famous cardiologist looking at his manuscript had an aha moment and rediscovered what Michelangelo already knew back in the late early 1500s, and that is how blood moves through the heart because the valves create a vortex. And here finally we have a rendition by Lewis. It's heartening to see this because it's about the level of my drawing skills. But here he's sketched sage grouse in his diary to show this kind of bird. No one had seen this before. They came across it. And they in fact discovered hundreds of new animals and plants as they led their expedition through the Midwest all the way to the Pacific Ocean. So again, we have this rendition. We look at this and we go, oh, we know that's a sage grouse. And here's a couple of artists. We do not know who they were, but because these products were created so long ago. The top one is a picture of a horse with arrows in it, suggesting that it was being hunted. And this is in prehistoric cave paint. This is prehistoric cave painting from, but we think 17,000 BC, done by a human. Another really interesting recording of data occurred in 1054 ADE or ACE, and that occurs in Chaco Canyon in New Mexico. And this is actually an overhang. When you walk up to this, you have to look up. And when you look up, you see this half-moon curve, a hand, and a star off to the left. And if you line that up exactly in July, and you point your telescope in exactly the direction indicated, you will see the Crab Nebula. And what we now suspect is that whoever painted this was recording the explosion of the Crab Nebula. And astronomers know that this happened on the 4th of July in 1054. So observing is critical. It's important that you do it carefully and accurately. Once you have that, you can make up a hypothesis. A hypothesis is a guess. It could be a question. It could be a statement of an explanation. And we'll practice these in class. Then you want to test your hypothesis. And you want to test your hypothesis by making more observations, by doing an experiment with a control setup and an experimental setup. You're only going to vary one thing at a time. That's really important. If you vary two things at a time, it gets very confusing. You can do it, but it's a pretty elaborate setup. Then you're going to analyze your data. And it's really important when you analyze your data that you organize it in ways that you can identify patterns. So we suggest to you, depending on the experiment, that you put it in a table, you graph the data, you make a diagram, or you create a series of drawings and photos that show some kind of progression through the experiment. And then you'll discuss sources of error. And these are not just human sources of error, but what kinds of mistakes could have occurred based on how you designed the experiment or how you collected the data. And then finally, having analyzed your data, you then take that data and look at whether it supports your hypothesis or it doesn't support your hypothesis. If it supports your hypothesis, you haven't proved that your hypothesis is true, but you have added weight to it being correct. If the data disproves a hypothesis, then you've shown that your hypothesis is incorrect, and now you can begin the process again, refine your hypothesis, and try a new experiment. And you do this process 1, 2, 3, 4, 5, 6, however many times, each time looking at your data, articulating a hypothesis, testing it, analyzing your data, concluding, modifying perhaps your hypothesis, and continuing on. So let's do an example. I have these two dogs, and one day I wake up and they both have diarrhea. I'm going, wow, this is not cool. If you've ever had to pick up dog poop from a dog with diarrhea, you know this is not okay. So I'm thinking to myself, what has changed? And then I realized, oh, I changed their food. So I'm going to hypothesize that the food has caused the dogs to have diarrhea. So now I'm going to generate an experiment. If the food causes the dogs to have diarrhea, then if I change the food back to their old food, then they shouldn't have diarrhea anymore. Makes sense. So how would I test that? Well, I'll keep one dog on the new diet, and I'll change the second dog back to the old diet. And then I'll simply observe and collect the results. No pun intended. I'll analyze those results and make a conclusion. I know you're all dying of curiosity about what happened. Fact of the matter is when I changed the dog food back to normal, the dogs still had diarrhea. It turned out they had a bacterial infection from having gone swimming the night before.